In section 9.1, we look at limits. And the first thing we're going to look at is finding limits using either a table or a graph. Finding limits is one of the fundamental tools to the study of calculus. So in order to understand what the concept of a limit means, we are going to look at the behavior of the function f of x equals x squared plus 3 as the x values come closer and closer to 2. In calculus, we write this as the limit, and then underneath the LIM you put x arrow 2, which mathematically says x approaches 2, and then in the parentheses you put either the name of the function or write out the entire function. And since this function is short and sweet and easy, we can put the entire function of x squared plus 3 into that. So we would read that notation that we have written here as the limit as x approaches 2 of the function x squared plus 3. We're first going to look at this concept by using a table. And we want to use numbers that are getting closer and closer to 2. But I don't mean things like 5, 4, 3 or 0, 1. I mean decimals that are getting closer and closer to 2. And if you think about the left side of 2, you are coming from 1 to 1.5 to 1.9, 1.99, 1.999. Notice that the number that is the closest to 2 is what gets written next to 2 in the table. On the right side of 2, you would come from 3 down to 2.5, down to 2.3, down to 2.1. Then you'd get into the smaller decimals of 2.01, 2.001. And again, notice that the smallest number of 2.001 is what gets written right next to the 2. When we are finding a limit, we do not care what is happening exactly at the 2. We want to know as we get closer and closer to it from the left and from the right, what values does it hold? So we're going to start on the left side and put 1.9 into the function x squared plus 3. So you're going to do 1.9, square it, and then add 3. If you do that on your calculator, you will get 6.61. Now we're going to put 1.99 in the calculator and see what we get in our function. And if you do that, you will get 6.9601. And then if you put 1.999 into the calculator, you will get 6.99601. If you look at those numbers, as we get closer and closer to 2, those answers that we got get closer and closer. I'm going to use this arrow to show approaching 7. Now let's go to the right side and do the same thing. We're going to start out by putting the number that's farthest away, 2.1, into the function x squared plus 3. If we do 2.1 and square it and then add the 3, we will get 7.41. If we put 2.01 into this function and find out what it equals, we will get 7.0401 as our answer. And by putting in 2.001 into the function of x squared plus 3, we get 7.004001. And so if we look at these numbers, again, we are getting closer and closer to 7. So what we say about this function in looking at it is that the limit as x approaches 2 of the function x squared plus 3 gives us an answer of 7. Because as we came from the right and from the left, we approached the same value. Now we're going to look at the same idea in a graph. This graph in the red is the function of y equals x squared plus 3. It's a basic parabola moved up 3 on the y-axis. What we want to know is what value of y does the graph approach as x approaches 2 from both the left and the right. So first of all, let's look for 2 on the x-axis. So we come over, here's 1, here's 2. Now, if we take this 2 and go up until we meet the function, and then think about tracing the function from the left and from the right, from both sides at the same time, what y value is that graph getting closer and closer to? Well, if you look, the y value that we're getting closer and closer to is the 7. So graphically, we get the same answer that we just got from doing the table. So again, we would say here that the limit as x approaches 2 of the function x squared plus 3 equals 7. The next thing we are going to look at is one-sided limits. That is the y value that a function approaches from only the left or only the right. We have some new things showing on example A. We are going to use this picture that I have given, and we are going to find one-sided and two-sided limits in this picture. When you look at example A, the limit as x approaches -2 is the same thing that we have been talking about. That superscript after the 2 means that you are approaching -2 from the left. And then f of x is just the name of the function because we don't know what this function equals, if it equals an x squared plus something or what it is. So we just gave it the name because we don't have the actual function written out for us. So on a problem like this one, what you are going to be doing is looking at your picture and think about if you were tracing this picture. Now remember, we are coming from the left. So if we were tracing this picture from the left side of the -2, what y value are we coming into? We are coming into the y value of 1. So the answer there is 1. So on question B, when we are asked to find the limit as x approaches -2, and then there's a plus superscript, that means from the right. So we are going to trace this function now from the right side of -2. Now, as we come into this thing from the right side, what y value are you coming into? That's always your question to yourself. What y value am I coming into? So this answer is also 1. On question C, we have the limit as x approaches -2, and we no longer have a superscript after the 2. that means that you are coming at the -2 from both sides at the same time. As long as you are going into the same y value from both sides at the same time, then your limit exists. Notice that we got a 1 both of these places. So our two-sided limit is 1. When you look at D, the question just says f of -2. That means what is the value of the function at -2? So you are looking for where is the solid dot at -2. Well, that's happening up here. So the value of the function at -2 is 3. What I want you to take away from this example is that the limit can exist, but it can be different from the value of the function. On question E, we are changing the value of x that we are approaching. So this time we are approaching +1 from the left. So if we look, here's +1. As we trace that function from the left, what y value are we going into? Well, that y value is 2. So the limit from the left is 2. On example F, we are approaching the x value of 1 from the right side. So if you trace this graph on the right side of 1, what y value are you coming into? That y value is 1. On G, we are looking at the two-sided limit for +1. So if you think about what happened, from the left side we went into 2, from the right side we went into 1, we went into 2 different y values. So what that means then is that the two-sided limit does not exist. And what we say when it does not exist is we just write D and E. You don't have to write an equals because equals means it's a value of some kind. So you just write the letters D and E to stand for does not exist. Example G wants to know what's the value of the function at the x value of 1. I have taken out my highlighting here so that you can see better. And what you are looking for the value of the function is at what y value do I have a solid dot? My solid dot is happening at the y value of 1. So f of 1 equals 1, where the solid dot is. I was running out of space, so I have put a clean version of the picture in here to start again, and we are looking at H, where we are asked to find the limit as x approaches +3 from the left of this function. As we come at +3 from the left, what y value are we getting closer and closer to? That y value is 5. So that limit equals 5. For problem I, we are approaching +3 from the right. So as we trace this graph coming at it from the right, what y value are we coming up on? It is again 5. On problem J, we are now looking for the two-sided limit as x approaches 3 for this function. When you look at both sides of 3 from the left and from the right, we are going into the same y value. So the two-sided limit is 5. On our last example, K, we are asked to find the value of the function f of 3. When you look at the x value of 3, you are supposed to be looking for where there is a solid dot. There is no solid dot at the value of the x equals 3. So the function does not exist at x equals 3. What I wanted you to see in this example is that the limit could exist, but the function does not. On example 2, we are asked to find the limit as x approaches 2 for the function of x squared minus x minus 2 over x minus 2. And we are asked to do this limit by using a chart. When you set up a chart, 2 should be in the very center. And I don't have really a lot of room to fit this in on my screen, so I'm going to kind of make it a 2-piece chart. So 2 is in the center. On the left side of 2, you want the number closest to 2, which would be 1.999. Then you go smaller to 1.99, and then you go to the next one out, which would be 1.9. Remember, we don't really care what's happening exactly at 2. We just want to see what's happening in these values as we get closer and closer to 2. So if you put 1.9 into the function of x squared minus x minus 2 over x minus 2, if you calculate that, you should get an answer of 2.9. If you put 1.999 or 1.99 into this function, you should get 2.99. And if you put 1.999 into the function, you will get 2.999. So we can see as we are approaching 2 from the left that the value of our function is approaching 3. So now we want to do the same thing for the right side of 2. So we have 2, and then the numbers to the right of 2 would be, remember, closest goes right next to it, 2.001, 2.01, and 2.1. And again, we don't care about exactly at 2. If you put 2.1 into this function, put it in using your calculator, you will get 3.1. If you put in 2.01, you will get 3.01. If you put in 2.001, you should get 3.001. So on this right side, these numbers are again getting closer and closer to 3. So what we can say here then is that the limit as x approaches 2 of the function x squared minus x minus 2 over x minus 2 equals 3. On example 3, we are asked to find the limit as x approaches 3 for the function f of x, where f of x is defined as a piecewise function. The first piece is 3x plus 6 if x is less than 3. The second piece is x squared plus 4x minus 6 if x is greater than or equal to 3. This is a very common kind of question in calculus in limits. You will see these a lot. What you need to remember is that you are looking for the limit as x approaches 3. 3 is being approached from the left using the function of 3x plus 6. That's all the stuff that's less than 3, the stuff that's to the left. The items that are to the right of 3 are the items that are greater than 3. So if you are using those items, you are going to use the function of x squared plus 4x minus 6. So I'm going to have to split this in half again just because I need to fit it into my screen. So for the left side, remember we are approaching 3. So 3 is our center number. To the left of that, we should have 2.999, 2.99, and 2.9. Remember, again, we don't care about 3 exactly. We want to know as we're getting closer and closer to 3. That's what limits always mean. These numbers are all less than 3. So the function that we need to use here is 3x plus 6. That's where you're going to put your values in. If we put 2.9 in for x on 3x plus 6, we will get 14.7. If we put the 2.99 in, we will get 14.97. Put 2.999 in, and we will get 14.997. So what number are we getting closer and closer to here? We are approaching 15. So now what we need to see is, will that also happen from the right? So when we are doing our limit from the right, the 3's in the center. The items to the right of 3 need to be 3.001, 3.01, and 3.1. We don't care about exactly 3. And remember, because these numbers of 3.001, 3.01, 3.1, they are all greater than 3, we have to use the bottom row of that piecewise function, the x squared plus 4x minus 6. So put 3.1 into this function, x squared plus 4x minus 6. If you do that, you should get 16.01. Put 3.01 in. You will get 15.1. Put 3.001 in, you will get 15.01. So what are these numbers getting closer and closer to? They are approaching 15. So what can we say about this function? The limit as x approaches 3. Now, when we have a piecewise function that has two different things, we just put the name of the function here in for f of x. We would just put the name in instead of the entire function. What y value were we getting close to from both sides? 15. If we had gotten two different answers on our pieces of the table, then we would say that the limit does not exist. In order for the limit to exist, you must approach the same number from both sides.